Dear students, today we can continue the revision process with the waves. We can go through the stunting waves and also the Doppler effect. Here, the reflection will happen between a wave and its reflected wave, and maybe treated as the very good aspect regarding the superposition principle. So here, when two identical progressive waves propagating in opposite direction superimpose, the resultant wave is called the stationary waves or stunting waves. Look, if the incident wave is represented as y is equal to a sine omega t minus kx, the minus kx means it is propagating along the positive x-axis. Then the reflected wave that can be represented as y2 equal to a sine omega t plus kx minus plus pi, y plus kx, it is propagating along the negative x direction, y pi there, it is inverted, and hence it is, we can write as minus a sine omega t plus kx. These two representations are very important. Then apply our superposition principle, you get the concept like this. And here, this is the amplitude, but it is independent of the term omega t minus kx or omega t plus kx. So we can reveal one concept: it is not a progressive wave, and hence the term the stunting waves or stationary waves. Look what happened after the mixing. Each and every particles of the medium are under vibration, under SHM in its position. There is no transfer of energy. The point where with minimum displacement, with the maximum density, with the maximum pressure, we call it as the knots. And look the location of knots at the positions x is equal to 0, lambda by 2, lambda. So that is x. And you keep in mind the very important concept. And look the antinodes. The antinodes means the positions having maximum displacement, minimum strain, minimum pressure, and at the location as lambda by 4, 3 lambda by 4, 5 lambda by 4, etc. And keep in mind, in total, the nodes and antinodes are alternate with the spacing of lambda by 4 between two nodes or between two antinodes with a spacing of lambda by 2. Keep in mind. So these are the basic concept. With our standing waves, we can memorize the very important concept: the standing waves on a string, a closed organ pipe and open organ pipe. Now the waves on a string. So this is nothing but the first mode of vibration. We can say the first harmonic. We can say the fundamental frequency. What is the simple relation? We can deal this simply as the frequency as velocity by wavelength. But how we can link that length with wavelength? Here, this is a length of the string. But you know the concept, the very important one, is lambda by 2. So you can just substitute it for L and you get the concept. And here it is the second mode of vibration, the second harmonic, but it is said to be the first overtone. So we can write as N2, the second frequency is equal to the velocity by this wavelength. That wavelength is nothing but here L. So it is double the first harmonic, double the fundamental frequency. And here we can say the third harmonic as the second overtone is 3 times of the first harmonic. So keep in mind, every harmonics are available with the standing waves. Every harmonics are possible with the string. Then what about the case for a closed organ pipe And keep in mind, if it is with a rigid boundary, you can sense it is with a node. If it is a not rigid, we can certainly say there it is with the antinode. So the first fundamental mode of vibration, it is this one with the frequency N1 by V by lambda. So how we can find it? A very important concept. So it is not a lambda by 2, and here it is a lambda by 4. The very important aspect as a lambda by 4. So lambda can be write as 4L. So that is the first fundamental mode. And what about the second mode of vibration? But keep in mind, the third harmonics are available there. That is a very important concept. From this to this, we can say it is just lambda by 2 plus lambda by 4. So that is nothing but 3 by 4 lambda, that is the length. So we can substitute it for lambda equal to 4 by 3. So it is nothing but 3 times of the fundamental mode. 3 times of the fundamental mode. Look, the third mode of vibration. In this third mode of vibration, see the 2 segments fully with lambda by 4. So that is the length is occupied by 5 by 4 lambda. So only the odd harmonics are available. 1, 3, 5. So second mode of vibration, the second harmonics, it is not available here. Here only the third harmonics are available. So the first overtone means the third harmonic. The second overtone means fifth harmonic. It is very, very important concept. So we can move to the next very important concept, the standing waves on open organ pipe. Look the figures. We can just compare it with a string. Everything are same. But here open ends, the open ends are with, only antinodes are possible. So at the middle there is a node, and on both ends they are with antinodes. So you can just go through the length. L is nothing but the wavelength by 2. These 2 parts together, it is lambda by 2. So it becomes so simple. As the frequency is velocity by the lambda becomes 2L. It is the same formula with the string. See the next, guys. Simple. And this segment and these 2 together give another segment. So it gives a wavelength lambda. So L is equal to lambda. So that is called the second mode of vibration, and is nothing but double the fundamental frequency. So similarly we can say the standing waves on an open organ pipe is with all the harmonics are available. All the harmonics are available. It is very important. Have the chance for a question from these 3 regions. So go carefully. The very important concept. See, we can move with 1 or 2 simple questions. A string with a mass density of 4 into 10 raised to minus 3 kilogram per meter is under tension of 360 Newton and is fixed at both ends. One of its resonance frequency is 375 Hz. The next higher resonance frequency is 450 Hz. Find the mass of the string. Here you should know 1 or 2 concepts. 1, the mass density is nothing but the linear density, the mass per length. And here, for a string, every harmonics are available. So here the 375 is say as N1. Then the next one means N1 plus 1 frequency, that is 450. So here the first one we can treat as N1 by 2L into root T by mu as 375. The second one, that N1 can be replaced with the additional one, N1 plus 1. So we can find the value for N1 as 5. Then we can easily find how much length is here by using this concept. Everything are here. But here we want to find what is the mass of the wire. So that is the linear density into the total length. So you get the answer 8 into 10 raised to minus 3 kilogram. A good aspect. See, a good question are waiting. A steel wire of length 1 meter and mass 0.1 kilogram and having a uniform cross-sectional area of 10 raised to minus 6 meter square is rigidly fixed at both ends. The temperature of the wire is lowered by 20 degrees Celsius. If the wire is vibrating in fundamental mode, find the frequency in hertz. It is given that Young's modulus of steel and the linear coefficient of expansion for steel. You know the thermal tension, it is nothing but the thermal stress into area. It is nothing but equal to y alpha delta theta into V. Now all the matters are here. So you get the answer as 48.4 Newton. By using that one, we can find the velocity as root t by mu as a 22 meter per second. Then for a fundamental node, you know L is equal to lambda by 2. Lambda is 2 into L. So we can find easily the frequency as V by lambda. So 11 hertz, that is answer. A good aspect, a good connection with the thermometry, thermal properties of matter. Look, the another question, a good question. A tube open at only one end is cut into two tubes of non-equal length. The piece open at both ends has a fundamental frequency of 450 Hz and of 675 Hz. What is the first overtone frequency of the original tube? So we can write, see, the open end got a frequency 450. We can write as 450 into V by 2L1. For the second one, both ends, that is 675 as V by 4L2. But we know the concept, the length of the tube is L1 plus L2. So we can write the first fundamental mode, that is equal to as a 3V by L1 plus the first overtone frequency of the original tube. So that is the first overtone of one end is closed there. So we can, the first overtone means it is nothing but the third harmonic. So 3 into V by the total length. So is equal to the total length is what? So L1 is what? L2 is what? You just get the answer at 20-25 Hz. The anti-correction, another very important one, and keep in mind the location of the antinode at an open end of an organ pipe lies slightly outside. The distance of the antinode from the open end is called the end correction. So that end correction is nothing but 0.6 of the radius of that tube. So keep in mind, look for the open pipe, you know, the tube, we have to find the location at 2, so we have to add 2 times. But for a closed, one end is only open, then you have to add 0.6 r to the length. This is a very important concept to keep in mind. A very, very important concept, the resonance column experiment. And that is used to find experimentally the velocity of sound in air. In this tube, the water is filled, the level of which can be varied. The surface of water can be taken as the closed end to the sound wave in air. If L1 is the first resonating length, we can write as L1 plus the end correction is equal to lambda by 4. For the second one, we can write as L2 plus E is equal to 3 lambda by 4. So you know all the concepts relating to that. You just subtract. Then you can find the velocity as a frequency into lambda. So you get the formula, and keep in mind. In the normal cases, the second resonating length is approximately 3 times of the first resonating length. The second resonating length is 3 times the first resonating length. In the normal cases, you can use as a shortcut. A good aspect, it is very important based on our KEAM entrance exam. The persistence of sound, that related concept, reverberation. The persistence of sound after the source has ceased to produce a sound, that is called reverberation. And the duration of this phenomena is called reverberation time. According to Sapien law, that reverberation time is equal to 0.16 V by A into S, sigma A into S, where A, the area of the sound absorbing material, and S, the coefficient of absorption, and here the V, the volume of hall. So you should know that while manufacturing halls or auditoriums, that constructors should use this concept. The Doppler effect for sound waves. You should know the notations we are used to here. So it's a simple concept, but you can wait one question from this area. We can just go through the different aspects of Doppler effect for sound waves. The first one, the source in motion, observer at rest, and medium at rest. So here the source moving towards approaches will increase the frequency. It is a very, very important concept. So n dash, the apparent frequency become V by V minus Vs into n. Here V is the velocity of the sound, V is the velocity of the source, and n the frequency, actual frequency. When the source move away from the stationary observer, the formula become n dash is equal to V by V plus Vs into n. You must go through the apparent wavelength also for the cases. The observer in motion, source at rest and medium at rest. See, if the observer moves towards the stationary source, approaches, the frequency should increase. So n dash is equal to V plus V0 by V into n. Observer move away from the source, V minus V0 by V into n. And keep in mind the effect of motion of the medium. You have to add or subtract with respect to the velocity of the sound depending upon the situation. We are waiting with the two important concepts. The Doppler effect in reflection of sound. And here, when the sound is reflected from the reflector, the observer receives two notes, two frequencies, one directly from the source and the other from the reflector. If two frequencies are different, then superposition of these waves will result in beats. It's a very important type of problems. Here the case 1. Look the location of the man when the source moves towards the right, and n dash d the direct apparent frequency, n dash the apparent frequency at a reflector, and n dash r the reflected apparent frequency. Then you can just write the formula. You know the every concept. If they are equal, then there is no beat frequency. If it is here, the two are equal, and hence there is no beat frequency. But the case is entirely different in the coming cases. See, and suppose the person is here. So the case becomes entirely different. So there is a difference in frequency. So that is called the beats. For the case we can say is in times the velocity source by V. Reason, the velocity source is so much less compared to the velocity of sound. See the very, very important concept. When the source and the observer move towards the stationary target, the very important concept. So there is a difference between that reflected waves, and hence we can just take the difference. We get the number of beats as equal to you must go through the last special point. It is very, very important. And keep in mind, there is no Doppler effect. If the source and observer are at rest, if they are moves with a constant velocity, if they are moving mutually perpendicular, and when the medium is only moving, and also when the distance between the source and observer is constant, in that cases there is no Doppler effect with the sound. It is very, very important concept. You can go with one good question. Two trains traveling in opposite directions at 126 km per hour, that means 35 meter per second. They cross each other while one of them is whistling. If the frequency of the note is 2.22 kilohertz, find the apparent frequency as heard by an observer in the other train before the train cross each other, after the train have crossed each other. Have to take the velocity of sound as 335 meter per second. So here, this is the concept at first one, and this is the concept on the second. You can just write the relevant concepts and you get the answer. A very important concept. So the apparent frequencies are different. So you must go through the initial video also. So then you can clearly you can say which topics are very, very important regarding the waves. God bless you. Take care.